Okay, we're going to start with 200 heavy particles in our container. We're going to take a look at the pressure, and we see that it's about 23 atmospheres. Then we're going to add 200 more heavy particles to our container. And we can see as we have more particles, we see more collisions, more force, so the pressure increases. We saw that the pressure went up from about 23 atmospheres to 46 atmospheres, so the pressure doubled. This is because we had more gas particles, which caused more collisions, which is more force, so the pressure increased. We changed the number of particles, we changed the pressure, but the volume and the temperature stayed constant. In a relationship, the moles increased and the pressure increased. This is a direct relationship. If the moles increased and the pressure decreased, that would be an inverse relationship. Because the moles increased and the pressure increases, that was a direct relationship, not an inverse relationship. So this is direct. We're going to start with 200 heavy particles in our container. But this time, instead of adding particles, we're going to make the container smaller. So as we make the container smaller, we see that because there's less space, there's more collisions with the particles. More collisions, more force, so the pressure increases. When we cut the volume in half, we saw that the pressure roughly doubled. This is because as the volume decreased, there was less space, so the number of collisions increased. More collisions, more force, so that is more pressure. We changed the volume, the pressure changed, but the number of gas particles and the temperature were constant. Because the volume decreased and the pressure increased, this is an inverse relationship. The graph on the left shows that as the pressure increases, the volume increases. This would be a direct relationship. The graph on the right shows that as the volume increases, the inverse of pressure increases. This says that pressure and volume are an inverse relationship. We know that pressure and volume is an inverse relationship, so the graph on the right is correct, and the graph on the left is not. Okay, I have the points plotted and the best fit line drawn. If we want to find the point where the volume equals 0, that's the volume equals 0, and the temperature at that point is the x-intercept. So we see the x-intercept is about minus 273 degrees Celsius. This is the coldest possible temperature because we cannot have a temperature where the volume goes below 0. This is how the Kelvin scale was invented. In Kelvin, you can have no negative temperatures. And 0 Kelvin equals minus 273 degrees Celsius. If we want to convert from degrees Celsius to Kelvin, we can use this equation. We take our degrees Celsius, we add 273, and that's how we get our Kelvin. For example, if we have a 25 degrees Celsius and we want to know how much Kelvin it is, we just add 273 to get 298 Kelvin. Going back to our graph, we can see as the temperature decreases, the volume decreases. So as the temperature decreases, the volume decreases. This shows a direct relationship between temperature and volume. This equation, called Charles's law, describes the relationship between temperature and volume. If we know the volume and temperature of a gas, if we change the temperature, we can calculate the new volume. Really important though, the temperature needs to be in Kelvin. Question 20 says we have a gas that is a volume of 600 mils and a temperature of 20 degrees Celsius. If we increase the temperature to 60 degrees Celsius, what will be the new volume? So before we do anything, we want to change the temperature to Kelvin. So we're going to add 273 to the 20 to get 293 Kelvin. We're going to add 273 to the 60 to get 333 Kelvin. Then we're going to do a little bit of algebra and solve for volume 2, and that is your answer. Okay, you guys should finish up to question 21.